Still waiting to send data. And we are streaming. Yo, Flurves, how are you all doing? Glad you could make it today. Thank you all for coming. It's good to see you. Tonight we're going to have a special one. We got a guest on. Andrew Johnston is going to be presenting to us on gravity, and obviously we're going to chat about a few things as well. But I really appreciate you coming on, Andrew. How are you doing, mate?
Yeah, I'm good, thanks. Very early for me, very late for you.
It's a normal time at least for me, so it's fine. But I appreciate
well,
you
that's
coming
right.
in.
Yeah, evening time for you. Yep.
But I appreciate you coming in, mate. I really appreciate you wanting to do a presentation.
Sure, no problem. Yeah, this is something that I was just for my own interest looking at and thought I might put a video together for it and present it to you. Why not?
Awesome. So what was your reason for wanting to do this specific topic?
Well, in the start of the video I say, but it was some conversations I had with Rachel in YouTube comments about a particular topic. I thought I'd look at it, find out a bit more about it, and thought put something together for Rachel to see what she thinks about it. And I thought it'd be great, now that I've done something on a new topic, it was a little bit of depth, present it to you and see what your responses will be to it. And just want to say, it's not specifically on gravity, it's more on evidence of a rotating sphere based on measurements of gravity. Anyway, we'll see it. It's only about 10 minutes long, and thankfully you've agreed we'll just play through it and uninterrupted, and then we can talk about it and some other subjects once it's done.
Awesome, yeah. So if you're ready, then we can watch it.
Sure.
Okay, I'm just going to say hi to everybody in the chat. Thank you for coming, guys. Really appreciate you being here. Please just hit the share and hit the likes as well. Thank you guys for coming. I'm going to start the presentation uninterrupted. I'm going to make it full screen.
Well, hello there. Recently I challenged Rachel50 to explain the variation in gravity that's seen that correlates with latitude. Now her objection was that maybe it hasn't been measured accurately enough to show that this phenomenon actually exists. Well, in searching through on the subject, I found this video by Geoscience Australia called the 2019 Australian National Gravity Grids Data Release. Link is in the description. Now, it's about an hour long, and a lot of it is not particularly relevant to the subject at hand, but there are some basics explained from about 4 minutes 45 to 7 minutes 30, and there's a longer section from about 28 minutes to 39 minutes, which details how they tease out the variation in gravity that's due to the underlying geology. Now, amongst many reasons, it's particularly useful for the mining industry so they can identify locations that are probably worthwhile digging up. Now, along with the release of data, there also was the introduction of a web portal to access the data. And here we can get the entire National Gravity Database on a map here, and it consists of about 1.4 million individual observations of gravity. We zoom in here on a particularly remote section of South Australia. We can see that there are gravity observations taken, roughly speaking, with a spacing of about 10 kilometres apart. Now, this is pretty typical for the country. In fact, most of the country has a spacing of about 6 kilometres or less, and there's only some smaller sections of the country that have up to about 10 or 12 kilometres of spacing. If we look at an area in central New South Wales, we can see a pretty typical part of the grid where the east-west spacing in this case is about 2 kilometres and the north-south spacing is about 5 kilometres. By contrast, if we go to the Tom Price region of Western Australia, where there's a little bit of mining activity going on, the higher density grid on the left side of the map here has a spacing of, I think, about 1 kilometre or less between those dots. And those lines are very intense observations, which sometimes have a spacing of less than 50 metres. Now, 1.4 million data points is probably a bit too much for our purposes here. So what I have concentrated on here is the fundamental gravity network. This is a network of around about, I think, about 900 observations. Now, all of these observations were done by absolute gravimeters, so they are to the highest standards possible on the during the time that they were taken. Now, if we look at one of them in particular, I'm going to pick this one down here at Busselton, south of Perth in Western Australia. We can see that it was visited and measured in 1967. and it was observed to have a strength of gravity of 9,795,750.82 micrometers per second squared. Now, that number sounds a little bit unwieldy, but if we think about that in terms of meters per second squared, it is 9.795 meters per second squared, a much more recognisable strength of gravity. Now, I'll also express it in terms of another unit called the microgal, which actually gets rid of the decimal points, makes it a little easier to compare numbers. And we see that at that location, it was 979 million microgals. So in rough terms, the strength of gravity on the surface of the Earth is just shy of 1 billion microgal. Keep that in mind, 1 billion microgal, when we move on to some of the next section. Now, where did the data come from? Well, starting in 1950 and proceeding to the mid-1960s, there was about 250 observations of gravity done across Australia using a pendulum absolute gravimeter. Now, they work on the principle that the period of oscillation of the pendulum depends only on the length of the pendulum and the strength of gravity. So if you're able to measure the oscillation period quite accurately and measure the length of the pendulum quite accurately, you can derive the strength of gravity at that location quite accurately. Now, from the early 19th century to the mid-20th centuries, these were the absolute standard in absolute gravimetry. Now, this only changed in Australia in about 1979 when this particular Soviet gravimeter was brought over to do some observations. This is a free-fall gravimeter, and it consists of a mass that is dropped through an evacuated tube. There is a laser interferometer in there to measure the location of the mass as it falls through the tube, and consequently the rate of acceleration that can be derived from those measurements. Now, here in Flat Earth Research, you are all very interested in vacuums, and the tube in this apparatus was evacuated down to a pressure of about 1 millipascal, and in other units that's about 1/100 millionth of an atmosphere, around about a 10 millionth of 1 psi, and in our favourite unit of all, it's around about 10 to the minus 5 torr. So remembering that the strength of gravity is approximately 1 billion microgal, this particular gravimeter was reckoned to be accurate to 15 microgal. So it's an extremely precise instrument. Now, it was only taken to 5 locations in Australia and 1 location in New Guinea. Now, that may not seem like much, but consider that the entire package of equipment was about 800 kilograms, so it's not very portable. And at each of those 5 sites, it did 2,500 drops of the weight. So quite a lot of time, quite a lot of data, and the purpose of it wasn't to remap the entire country. The purpose was rather to provide a more accurate datum to which the older data could be tied and to which new data could be tied. Of course, this type of equipment has stayed in use since then, but is much smaller, much more portable, much more affordable, much quicker to use, and much more accurate. In the early 2000s, Geoscience Australia started using some that were accurate to just 2 microgals. So extremely precise instruments. So now to the actual data. So Geoscience Australia released the entire 1.4 million observations. Now, I've taken about 400 of those, which were done by absolute gravimeters, and that are part of the fundamental network. Now, interestingly enough, there are still some observations that are included from the 1950 surveys. They are still considered good enough to be included today. Now, amongst all the different parameters, quite a few of them, that each data point has, the ones I'm particularly interested in is the latitude of the observation site and the strength of observed gravity at the observation site. Now, I've also taken the geoid height, which in rough terms is the height above sea level, though not exactly, and I'll come to the reason why I've taken that in a moment. But the first thing is that we take the latitude and the observed gravity and we plot them against each other, and we get this. We can see that we have a quite clear trend that as we go from minus 35, which is 35 south latitude, to around about minus 12 latitude towards the equator at the top of Australia, we find that gravity decreases. in quite an obvious pattern. Now there is a bit of spread amongst all these numbers, and that's where I've then gone and done some height corrections. Now the reason being is that because of the oblate nature of the spheroid that the Earth is, we find that the closer you are towards the equator, the further you are away from the centre of mass of the Earth. This picture is quite exaggerated. And also, the further you are above sea level, so you're up on top of a mountain, the further you are away from the centre of mass of Earth as well. So I've done some very crude calculations to control for that, but by doing that, this set of data becomes a much tighter match. So still, what we can clearly see is that as you head up towards the equator, gravity gets less, and that is exactly as predicted by a rotating sphere. Now, of course, the globe has a perfect explanation for this. We can think of gravity as mass attracting mass, and that's the reason why objects are drawn towards the centre of mass of the Earth. And the variation that we see with latitude can be explained by the Earth being a rotating spheroid and the different amounts of centrifugal force that is produced because of that. Now, to Rachel's objections, are the measurements perhaps not precise enough? Well, we see here on the variation of observed gravity with latitude, this variation happens in about the third or fourth figure of precision. Now, if we remember from early on, the equipment that's being used to make these observations is actually precise down to about 8 or 9 figures, so definitely precise enough to see the 4 figures sort of variation. Now, are the observations not accurate enough? Well, the overall aim of this is to understand something about the underlying geology. So in order to do that, we do things like take into account known factors, things like latitude, the oblateness of the Earth. There are other factors, which I won't go into, but once all those factors are taken into account, what you're left with is hopefully enough to identify the underlying geology for one particular purpose, and as can be seen by the amount of time and effort and money that mining companies spend roaming around their lands using gravimeters measuring gravity, if it wasn't worth it, they wouldn't be doing it. So it is definitely accurate enough to measure the very small variations due to local geology. Definitely accurate enough to measure the variation due to latitude. So, what is the flat Earth explanation for this? Well, we often hear that gravity is actually explained by density and buoyancy. Well, if that were the case, then it shouldn't vary anywhere on Earth. So this gravimeters used anywhere on Earth should produce the same numbers. After all, it's the same tube evacuated to the same level of vacuum. It's the same mass being dropped in it. It's the same interferometer measuring the falling of the mass. It's the same equipment doing the measurements and the calculations based on that. So it should produce the same results all over the Earth within a small range of variation. But as we can see, it doesn't. It produces different numbers. So what's the explanation? So, thanks for watching. It's all over for the globe. There's no coming back from this one.
Thank you very much, Andrew, for that presentation. It was interesting. So, do you have anything further to say on that?
Yeah, well, I mean, the short summary is that the free-falling mass in an evacuated tube is measured. The acceleration of that mass is measured very accurately. You don't have to call it gravity, call it downward acceleration, but it has been measured in Australia in over 1 million places, and it shows clearly that the the rate of acceleration, I call it gravity, varies quite clearly by latitude, and it matches exactly what is expected from a rotating sphere. So I'm just wondering, give me your thoughts. How do you explain that? Or, I mean, do you deny that the measurements are accurate? Do you deny that they're doing this work? Have you got an explanation for why the numbers vary with latitude?
No, gravimeters definitely work. I mean, I know even by us, the mines use them for the density deposits. That's how they know where the dense objects, if they're going to have more gold or platinum or whatever to mine. So gravimeters definitely work. But would I say it's gravity? No, I wouldn't necessarily say that. Obviously, you are correlating it with the centrifugal force of the globe, hence why it's a geoid. So it's fatter at the poles. I mean at the equator, so therefore that's where you have a variation at latitudes, as you say. Obviously, you have to beg the question for that to happen. Would I be able to explain it why density would show it differently? Not really, because I didn't really make a claim that density will work with gravimeters, although they did remove the medium, hence why it's in a vacuum. But I got some questions about the gravimeters though. Do they have any plating for magnetism?
I don't know.
Or temperature changes?
Well, I'm sure that they things like the laser interferometer has things like that, so it produces similar things. But the thing is that the large scale variation in numbers, not the small scale related to geology, that's really deep in the numbers. The large scale at the third and the fourth figure varies by latitude. Now, if that was something to do with magnetism being different, then we'd see the magnetic field relate to latitude like the gravity measurements do. If it was related to air pressure or temperature, then we'd see the same thing. We'd see out in the deserts of Australia, we'd see different measurements, vastly different measurements to those up a cold mountain in the Alps of Australia. But we don't. We see that the raw measurements from these machines produces that picture of Australia I showed that had that gradient of colour from top to bottom, exactly in line with latitude. The raw measurements of those machines come out like that. Now, I'm going to pull up a picture and show this to you, which I didn't include in the presentation. Just allow me to get a screen going, because I thought this was kind of interesting. So now, are you seeing a graph there on screen?
Yes, yeah.
Fantastic. So this is a graph. If you look down the bottom, maybe you can't see it, maybe it's a bit small, but it's from the 5th of May, 6th of May, 1979. This was the Soviet gravimeter that I showed that black and white picture of that was brought to Australia.
With the pendulum.
And these,
oh no, that was the new one, the dropping.
And that Soviet one at the time in 1979, that was new technology. And so that's why it was brought all around the world to do different measurements, because it was new and it was far more accurate than the pendulum ones. Now, this might have been from the Hobart measurements, I'm not sure, but it's one of the Australian measurements. Now, if you can see in that graph, ignore the wavy line. What you need to see is those little vertical lines with the circles in the middle of them. These are the individual sets of, I think it might be 200 or 250 drops per session, and each session, the circle is the average of those drops in terms of the strength of gravity, the speed of the acceleration, and the little bars up and down are one standard deviation either side. It's like a measurement of the amount of error that they get in these drops, because they take lots of drops and they average them. Now, these, if you just focus on the circles that go up and down, and they kind of follow this sinusoidal kind of line through here. Now, this sinusoidal line is what is the predicted solid Earth tide. Now, that is the slight flexing of Earth with the movement of the sun and the moon. Just like the tides in the oceans, the Earth itself, because it's not absolutely rigid, flexes a tiny bit. Now, over on the left side, you can see the scale. On the very far left, the zero line, it goes up to plus 50, it goes down to minus 100. These are microgals. These are the 8th and 9th digit of precision. This machine is measuring variations at about the 8th digit of precision. So these are very, very small variations which are related to the Earth buckling ever so slightly because of the gravitational variation with the sun and the moon moving around us. And this thing is measuring it down to 15 microgals or thereabouts. The variation that we had in, whoops, that's not the right thing. The variation that we had in latitude is in the order of 100,000 or 1 million microgals. So the variation we see on this picture, sorry, that's changed to that colourful picture, has it?
Yeah, it's got the colourful picture.
Yeah, it has. Okay, sure. Sorry, just making sure the screen share is working. So the variation here is only in the 3rd or 4th digit, and this machine is measuring consistently with what is expected from the solid Earth tides that are way down in the 10 microgal range. This graph is showing variation in the millions of microgals. So what is causing this huge, huge variation, far, far greater than the precision of the machine? You know, forget about local geology, forget about Earth tides. What is causing these really big numbers to happen? If by 3 or 4%, then there's something wrong with the machine, unless there's something else going on. And none of this variation relates to height above sea level. None of this variation relates to the change in the strength of magnetic field. Not at all. It is totally correlated with latitude. So I really want to see how do you explain that?
Okay. I don't know if you know this, but I work with scales a lot, and I can move my scale 10 centimeters from its original spot, and I have to recalibrate it because it gets out of calibration. Would you know if they calibrate those gravimeters every time they set them up?
Well, of course they do. The thing is, these are absolute gravimeters, so there's really essentially no calculation. There's a very, very fast and accurate clock, and I guess at the time in the 70s, that was the advent of atomic clocks, and a laser. The tube is evacuated to a certain rate. It is extremely accurate. It's essentially not calibrated against anything. They drop a mass and they measure it falling. Your scales are not going to measure a difference of 15 microgals. There's no chance of that. Your scales are not a scientific apparatus. Your scales, they might be good for trade, but they are not nearly as accurate and precise as basically what these are. Scales and gravimeters are kind of in the same class of thing, and yours are just nowhere near that level of accuracy.
I would agree it's not made to be the accuracy of the gravimeters, but my point is that you have, just by moving it, you have to calibrate. And as you say, they don't calibrate the gravimeters. Also, another question is that, let's say you use the gravimeter at one spot and you decide to change the altitude in exactly the same spot. Would you get a different reading?
Yep, you'll get a lesser reading. I could show you, I won't go into it, but I could show you. Just when I was doing my own exploration of the National Gravity Grid, I picked a location. I actually picked a location in Canberra, that's the capital of Australia, where there are a handful of observations done with absolute gravimeters, done within a few kilometres of each other, so essentially at the same latitude. One of them was down at water level. There's a lake in Canberra. There's a couple of down there, and then there was a couple of done near the tops of some mountains that are a few hundred meters above this exact same lake. And sure enough, the measurements were a very, very small amount smaller. So it correlates with latitude, and it's correlated with altitude. And that's why in my presentation I took that raw data and made latitude and altitude compensation for them, and the data got a whole lot closer. So yes, altitude does make a difference. Altitude is not going to make the difference of 0.5% or whatever that nice colourful rainbow graph does. Those altitude differences are a whole lot smaller.
Okay, and would you agree it's programmed to give a certain reading, the gravimeter? Does it have?
Not at all.
Has it got some kind of programming in it to have a reading?
It measures the falling mass. It measures the position at a really fine time scale. I don't know how much fine time scale, but it measures a mass falling in a vacuum. Now there's no other effect on that falling mass. No matter where you are, it's the same vacuum inside there, so the same medium if you want to talk about relative density, and it's got a laser interferometer bouncing lasers up and back off the mass as it falls down, measuring the position, and from that working out the acceleration.
And do they do multiple readings at one location, or do they just do one and then go to the?
Yeah, no, that Soviet one. Each one of those sessions of readings that I showed that sinusoidal graph on was about 250 drops, I think, at each session was 200, and they did it over the course of a day. So they did 2,000 or 2,500 drops for that Soviet gravimeter at each location. Now the newer ones
so it would be an average then. It wouldn't be a set because it does change ever so slightly with each drop. So it's an average.
Yes, it's an average. But
so then it's not gravity then, because gravity would stay exactly the same, and you wouldn't have to make a average. So it could be something else, not gravity, correct?
Well, no. Now the reason is that of course no piece of equipment is perfect. So there's going to be a variation. Now, can you just show it? I'm sharing again. Is that coming up?
Yes, it's on.
Right. So as I pointed out, now remember the scale of this is tens of microgals. Remember, gravity is about 1 billion microgals. So each of these little vertical lines, the circle is the average of that, say, 200 drops, and the bar going up and down is one standard deviation either side. Now, you may not know statistics, but on a normal distribution, 95% of observations fall within 2 standard deviations of the average or the mean. So if you were to extend those bars twice as far up and down, 95% of each of those bunches of 200 drops fall within 2 lengths of that bar either side of the circle. And we are talking 15 microgals. The level of variation with latitude is millions of microgals. So yes, the machine does lots of drops because of that inaccuracy and margin of error of equipment, but they average it and they have a very, very tiny spread of measurements for each one of those sets of drops. They match the predicted theoretical solid earth tide, which is again down in the orders of tens of microgals, and yet the variation in measurement back way up at the 2nd and 3rd digit, not way down at the 9th digit, is showing this level of variation.
Yeah, but like I said,
what else could it be?
Like I said, so you do agree then it's got variation, so they have to have an average. If it's supposed to be,
but you look at how small that variation is, though.
But
that variation might be 10 to 20 microgals for each.
Doesn't matter. Is
group.
Gravity supposed to be constant or not?
Yeah, but our machine's perfect.
Well, if you're making the claim
our
that it's
machine's perfect.
If you're making the claim that it's very accurate and nothing's changing, then yes, at the accuracy level that it's supposed to be doing, then yes, it should give the same reading no matter how much times you're dropping it. The fact it changes ever so slightly shows it could not be what you're claiming it to be, and then it's correlative, not causative. So we can go into the realms of what is it reading? Who knows? All we do know is gravity, nobody even knows what it is, and gravity is not even seen as a force to be able to cause that mass to accelerate.
It doesn't matter. Call it downward acceleration. In the entire... Now, the video that I used was about an hour long from Geoscience Australia. In that entire video, they mentioned the word gravity plenty of times. They never mentioned relativity. They never mentioned space-time bending, because in the normal, ordinary circumstances, we can treat gravity in a Newtonian sense. But anyway, going back to your point, what's it measuring, why there's variation? The variation in measurement, again, is in the order of tens of microgals. The strength of gravity, the strength of the downward acceleration, is 1 billion microgals. So any measurement equipment is going to have a margin of error, and you're going to get different measurements every time you use it. And the level of precision of this equipment, firstly, is in the order of 100 million times finer than the variation that we measure. And the accuracy, as in how consistent those numbers are every time you drop that thing, it's within, again, about that 100 millionth of the average, maybe 10 millionth of the average. So you get tiny, tiny differences in readings over the course of 250 drops. And then you give an average for that. But that's what you do in anything. Anytime you're well familiar with surveying, you don't just take one measurement, because one measurement could be inaccurate. You take lots of measurements, 6, 12 measurements, whatever it is, and you average them because of that tiny inaccuracy in each measurement, and you average them to hopefully get a more accurate thing. Again,
but like
the variation in gravity is millions of times bigger.
But
so why does it correlate with gravity?
Remember in your presentation you said they have to account for certain correlations, correct? So okay. What I didn't go into deeply in my presentation is when you take those large numbers, 900 million whatever microgals, this is what geoscientists do, and PhD Tony will be able to talk about this much better than I can. You take out the known variation due to latitude. You take out the known variation due to altitude. You take out the known variation due to centrifugal forces being different at latitude. You do some other things, Bouguer anomalies they're called, and you tease out all the things that you know about the Earth that are going to give variations in the rate of its downwards acceleration. But that's
and at the end of all that, you end up with the data of what you don't know about the Earth, and that is the underlying geology.
But that's my point. You already begged the question that the Earth is rotating, so you've done correlation-based...
so the proof of the pudding is in the eating, as they say.
Sorry, but like I said, you've already begged the question that the Earth is rotating, so you're making... how can I put it? Correlations based on that to fix for that anomaly, you're already begging the question that you have different amounts of force being attributed at different latitudes. You see what I'm saying? You're already creating your own correlative data and coring it with circle reasoning, gravity at different latitudes. So you're just literally doing correlation, circular reasoning.
Okay, so it's not begging the question, it's making assumptions. Now, and like I just said, the proof of the pudding's in the eating, isn't it? And so the proof that this is working, and I'll explain it in a second, is that mining companies, and you can well know it in South Africa, they use this equipment to find deposits that are different from the surrounding
density
rocks.
Deposits,
so,
yeah.
That's right. And so how do they find that? They find that by taking these measurements of 9 figures of precision, and then they assume the Earth is a sphere, assume that gravity works the way it says, assume centrifugal forces, assume these Bouguer anomalies, and a couple of other things, right? And they find this data that says there's something different in this location, and there's something different in this location, something different in this location. Go dig it up and see if something's there. So I'm almost done here. So if those assumptions about the shape of the Earth and how they affect gravity were not true, they wouldn't be able to map out these anomalies based on geology, go dig them up, and find that there's something interesting there. Similarly, in locations that are currently being mined and that historically were found just by people digging around until they found something good, they are also shown on these maps. So it's like they can weed out the large-scale stuff due to the shape of the Earth and find the really, really small details that tells you, hey, there could be some petrol here, some oil, there could be diamonds here, there could be gold here. It's pretty complex stuff, but if they weren't making those huge, huge changes because of the shape of the Earth, they wouldn't find the really, really small details as to do with these small deposits. So the proof is that the technique actually works.
Okay, but do you know anything about diamagnetism?
So if it was anything to do with magnetism, they'd know about it.
No,
Geoscience Australia.
Diamagnetism. Do you know anything about diamagnetism?
I'm not an expert. I'm not much of an expert in magnetism. I'll agree that. But if it was some other effect, right, that was causing those huge differences in relation to latitude, again, thousands, hundreds of thousands of microgals difference related to latitude, then why is it correlating with latitude? Forget about the little things like a gold deposit somewhere. That's the really small numbers. Why are the huge numbers varying with latitude?
Okay, but
why do they correlate so much with latitude?
Like I'm saying with my diamagnetism, you would understand different deposits would have a different amount of either magnetic pull or a magnetic push. That's why you have ferromagnetism, paramagnetism, and diamagnetism. You would understand gold would have a difference in the magnetic pull than it would, let's say, iron, where iron is paramagnetism, where it pushes away. You understand? So it would give a different reading. Now, what is the object that they let falling in that vacuum?
I don't know. Probably a metal. However, I know you're going to talk about magnetism.
What kind of metal?
I don't know. Probably something that's not ferromagnetic. I don't know. The point is, though, if they're finding... Okay, the variation related to geology might be in the order of thousands to tens of thousands of microgals. So why are they seeing a latitude correlation that is in the order of hundreds of millions of microgals? Is the Earth more magnetic or less magnetic towards the equator?
I'm not saying there is anything that's got to do with latitude. You correlating... Listen, you're begging the question of latitudes for a globe and then correlating the data that you had to already fix to cause for a globe because you had the assumption of a rotating geoid. You understand? You already begged the question, so you already doing your fixes based on that correlation of believing it to be a globe. So it's a rigged system.
These are raw measurements of the speed of acceleration, the rate of acceleration in a million places around Australia, in literally billions of places around the Earth. Now, you can't deny latitude, whether you want to talk about how latitude's fine. You can't deny latitude. There's an equator, there's a pole. I claim there's a South Pole, you claim there's not, whatever. But the correlation on that picture that I showed of Australia, there is a clear correlation with the distance from the equator. Now, that is raw measurements. So what is varying across the Earth to such a large degree? I say it's the strength of gravity because of the way gravity works and because of latitude and because of a rotating sphere.
Okay.
What is your explanation?
Okay,
You've talked
Andrew,
about magnetism, you've talked about other things. Why does it vary so much? Clearly by latitude.
Why do some countries have more deposits than others, Andrew?
The deposits, the gravitational variation with deposits is in the order of hundreds, thousands, tens of thousands of microgals. The variation that I've shown in that picture in relation to latitude is in the tens to hundreds of millions of microgals. So South Africa's got lots of diamonds and gold. So what? Australia's got lots of gold, I think. I don't know. We've got lots of iron ore deposits.
So have you realized at different latitudes, most deposits vary based on latitude, as you put it?
So there's more gold in the north of Australia than the south of Australia because of that rainbow graph that I produced. What is there gold across all of northern Australia and oil across all of southern Australia? Why does it vary?
Some countries are just more richer than others with deposits. Is that gravity related, or is that just based on the geography of the Earth we live on?
Is that it? Now is that rainbow picture showing up again?
Let me just put it up again.
Just present it. I'm just going to show you.
And it's on, yes.
Okay. Is that picture where it's blue in the top and red in the bottom, is that showing the difference in related to geological deposits? Or is that showing a very large scale difference in gravity, a difference of in the order of a tenth of a percent or something, which is quite large? So you're saying that this picture is showing that there is, for example, the green might be gold deposit, blue might be oil deposit, red might be diamonds.
No, that's not what I'm saying. You do understand. You don't, even in the mines here, where let's say you go to a gold mine. It's not 100% pure. It's not 100% pure. It's not 100% pure gold that gets mined. You have to refine it to get the gold out. It has different minerals and deposits entwined inside it. So if I go and take, let's say, a gold mine close to me and a gold mine 5 hours away from me, the deposit is different. Both have gold, but the minerals they're entwined with is different. Do you understand that could be what is actually going on? It's not the reading gravity, then it could be many different things. And that's what I'm saying. You're just begging the question, and then you're affirming the consequent basing on begging the question, and all your data has come around from you already correlating. I believe the Earth is spinning, so let's quickly make some correlation fixes for that. And I believe gravity is a force, so let's make correlation fixes in that. We've already explained gravity is not a force. It can't be a force. And the gravimeter works on the principles of relative density. So I'm asking again, what is the actual object's content of the object they're dropping in that vacuum? What is the vacuum made out of? There's so many different variables you're not accounting for, and then you're just making correlations for your globe and saying, you see? It has to be a globe.
Okay, again, you're not understanding the scale of it. I'll give you two parts to this answer. Again, as I've said plenty of times, you're not understanding the scale. The thing measures down to 15 microgals. Gravitational variation that's teased out to do with geology is in the order of thousands, tens of thousands, maybe 100,000 microgals. The variation in latitude, as we can see across the vastness of Australia, north to south, is in the order of hundreds of millions of microgals. So the variation is not to do with geology, doesn't produce the variation in the second and third digit. It produces the variation in the fifth, sixth, seventh digit, those sort of things. Now, secondly, if it is relative, towards the end of my presentation, if I said, if it is relative density disequilibrium, that vacuum tube, I guess it had air in it. I don't know what it had originally, whether they do something like put nitrogen or something like that into it, something not reactive. But it's down to it's evacuated down to, I think, 1 millipascal, I think it was, every single time. The mass in it, whatever sort of metal it is, I don't care, it's the same metal that was dropped 200 times over the course of an hour in that Soviet one. And over the course of a day, they dropped it 2,000 times and measured that. They moved it to another place in the country and they dropped it another 2,000 times and measured that. It's the same equipment with the same parameters, the same vacuum, the same tube, the same mass falling. Mm-hmm. So if things falling is because of relative density disequilibrium, it's the same thing every time. It should produce the result within that margin of error of a piece of equipment, wherever it is over the country. So what is it?
Because
so if it's producing different things, if it's just, I'll let you go in a second. If it's producing different numbers and really large scale, 0.5% difference between the top of Australia and the bottom of Australia, what is it about density disequilibrium? So your density disequilibrium is something to do with the density of the mass, the density of the medium. It's the same mass, the same medium. Why moving at a location makes a difference in what it measures.
Again, like I said, you guys have already rigged the system. You're doing correlative fixes for your belief on a latitude. So the system is already basing its fixes based on that. So if you're going to, I must make, I'm trying to think of the right word. I need to account for latitude because of my belief that the Earth is rotating. They've already set it into their system. That's what the gravimeter is, just doing what is told by it. And like I said, if you realize that if, let's say, you drop something 200 times, we have such thing as thermal transference, this entropy, this thermodynamics still at play. Even if the object is dropping in a vacuum, there is still some sort of thermal transference. So there's going to be something happening that's going to change the environment it's dropping in. That gravimeter itself, it has temperature variations throughout the day while they're dropping it that 200 times. The day it gets hotter, it gets colder. Like I said, you don't know if they even take magnetic fields into account. Heck, you can sit still and a magnetic field can change while you're staying still. There's many things that can be a variable for what's actually causing that. And how often do they do these readings? Or is it just the guy took it in 1979, therefore let's put in the data and then keep it that way? Or do they go and redo that same reading, let's say 10 years later?
They have done 1.4 million gravity observations throughout Australia. Now, a lot of them were done by relative gravimeters. I won't go into how they work. But
that was the pendulum. That was the pendulum.
No. That was an absolute one as well. Okay. The relative one is generally a weight on a spring. And you take it to a location. It's like with surveying, where you go have a known location, and then you offset yourself to but there are well over 1,000 readings across Australia since 1950 done by absolute gravimeters, and they take longer to do, and they have more accurate results. So there's plenty of results done. It's done in known locations because it was new technology. It was more accurate and more precise. They took their old readings from the pendulum gravimeters of the 1950s and 60s and worked out that with the new Soviet gravimeter that was more accurate, they needed to make a slight adjustment. Now, the adjustment was very small. It was in the order of, again, tens of microgels, okay? And so their old readings, they said, hey, our old equipment was off by a little bit. Let's move it a little bit. And newer equipment comes along that is more accurate. Now, that Soviet gravimeter was accurate to 15 microgels. The newer equipment that Geoscience started using 20 years ago, they have one piece of equipment that is accurate down to 2 microgels, so 7.5 times more accurate than the Soviet one. And they look at their old data and see how it matches with the new data, and they make slight adjustments to that old data to make it all match and make it all nice. And you're nodding your head and smiling.
Yeah, because you're doing exactly what I said they do. They make it to match.
Again,
so
listen to the scale of it.
Then.
Listen
I don't care about the scale. The point is, they're making the data to fit their already biased assumption.
They know that their old equipment, the measurements, like just say they did 50 measurements with their old equipment, the measurements, relative measurements between those 50 measurements done by the old equipment are good, but the overall piece of old equipment, they found out that it wasn't calibrated exactly perfectly as our new equipment says. And they go, well, all those readings, we need to move them up a tiny bit. It's like you find out that your ruler isn't scaled properly. All the measurements you took off that ruler, you just rescaled them slightly. Now, again, you're saying you don't care about the scale. The scale is important. Some of the measurements of Australian gravity done with the newer equipment, the end result of that is they went to their old measurements taken from the 90s and 50s with the pendulum, and they moved those, I think, up or down by about 50 microgals. So again, a very, very small amount when the strength of gravity is 1 billion microgals. They took their old measurements and went, they were great measurements, but our overall datum for that measurement was off. Well, let's move it up by 50 microgals. Again, 50 microgals versus the strength of gravity of 1 billion microgals, and I'm showing variation with latitude in the orders of tens to hundreds of millions of microgals. So these slight changes with the gravity datum over the decades does nothing to the variation at the second and third figure. Now, there's also gravity variation is postulated because of changes in groundwater. They go back to exactly the same site decades later and find that they've got slightly different readings. Again, very, very small variations. And it's not just the old equipment wasn't precise enough, but the groundwater situation changes year on year over the decades as we have droughts and as we have more normal levels of rainfall. But these variations, just like the variations because of geology, are very, very small compared to that big rainbow picture I showed you that shows a clear variation at absolutely huge numbers related to latitude. And all you're bringing up, is it temperature differences? Is it geological differences? Is the equipment getting hot over the course of the day? No, it's being used inside. That the Soviet one was used inside in scientific laboratories. You've got nothing that explains why there's this huge variation in numbers that just happens to correlate with latitude. Flatzoid, you've got no explanation.
So you're saying let's say magnetic fields don't correlate with latitude?
No, they don't. Magnetic fields don't. You look at a magnetic field strength.
You know what magnetic declination is, Andrew?
Yes, absolutely I do. I do a lot of navigation, so I know what magnetic declination is all about. And
does that change with latitude?
It's not correlated with latitude, not at all. You go look at a magnetic declination map. It doesn't look like latitude lines.
But it changes with latitude. It's not the same at every latitude, does it?
It changes with location.
Yeah, at latitude.
But
no, really. You know how magnetic field works.
Don't worry. I know what magnetic declination is all about. Trust me there. I know what that's all about.
So, like I said, there's many variables that you're not taking into account, and the bottom line is you guys set a bias on what you're saying it is, then creating your data to fit that bias, and then saying, see, it's gravity. It's just
I've just put up a magnetic declination map, and there's nothing that correlates with latitude. The lines are all over the place. If that was causing the
on
effect
a Mercator map,
of like,
is that on
it doesn't matter what map. Latitude lines on a Mercator map are straight. Doesn't matter. You pick up a magnetic declination map of Australia, and you see that the magnetic declination lines, roughly speaking, actually kind of run more north and south. And so why would it? What
latitude?
So
yeah.
You have a bit. Yeah. I'm going to hang on.
Do you know the? Yeah, you can share that because I want to show you something.
Yeah, that's all right. Where am I going to find that? Oh, I see what's this. I will see what's going on. This one. Can you bring that? It's show my map, my screen.
There we go. On a
there
Mercator.
We go.
So that's on a Mercator.
Yeah, it doesn't matter what projection it's on. If you look at Australia, those lines that run across Australia are running roughly north and south. So magnetic declination varies as you go east to west in Australia. So why does gravity vary by north to south?
So stick this on an AE map, and which way is the variation going?
It's those red lines across Australia are still running north and south.
Stick it on an AE map. Which way are those lines?
It doesn't matter. North is towards the North Pole, It doesn't really matter. It's not going to suddenly correlate with latitude. Latitude on the Mercator here is directly left and right across the map, which is what the variation happens as you move north and south in gravity. So
if you're saying that, if you're closer to a magnetic field or further away from the magnetic field, does it give you variation?
This is not strength of gravity.
Does it give variation, Andrew?
Flatzoid, this is a complete red herring. This does not match. The lines on this map, and if you looked at a magnetic field strength map, none of those lines look like latitude lines.
You're not answering me. If you further or closer, it's just a simple yes or no. If you further or closer from a magnetic field, does it affect...
Get me a magnetic declination map. Get me a magnetic declination map and get me a magnetic field strength map, and show if that shows the variation in latitude that I showed in gravity. It doesn't. Yeah, sure. You get further and closer away, things vary. Not a problem. Are you saying that the equator is magnetic?
No, I never made that claim. I never made a claim that anything's magnetic. I'm just saying the variables you aren't taking into account.
So, if the magnetic field strength was what was causing that variation in latitude, then the magnetic field strength would hang on.
Okay, and then I got another question. Do they use the exact same gravimeter everywhere they go to make that reading, or do they have different gravimeters? Because I'm sure there's not
different
one...
gravimeters. Don't worry, there's different.
Great.
Yeah, and
so let's... I want to explain that. So let's take like a Nissan GTR. They're usually hand-built. They use exactly the same machinery, the same mechanics, the same everything, and the horsepower is different from every single engine. Now, would that give a different reading? Like your gravimeters are different gravimeters. Do they give different readings?
Right. So as I've said in my presentation, there were pendulum gravimeters used in Australia, and then there were absolute freefall gravimeters used in Australia. And that the figures produced by the freefall gravimeter, that Soviet one, led to a minor change in the datum of the old data. Since then, there have been many more freefall gravimeters. I know Geosize Australia has a couple of much more accurate ones, and they produce data that, again, is within 10 or 20 microgals of the old data. And so they just move the old data 10 or 20 microgals. You're still not explaining how a 10 or 20 microgal difference between one piece of equipment and another piece of equipment produces the 100 million difference in microgals.
And how do they move this microgal, Andrew?
What do you mean move microgal? Microgal's a measurement.
How do they move it? You said they move the microgal. How do they move it? Do they just decide to stick it into their calculations? So they're working out the average. Yes, it's per centimeter squared. Yeah, but how do they?
Microgal. Yeah.
But how do they move it?
I don't know what you mean by move microgals.
You said it. That was your words. They move the microgal.
Oh, they adjust the datum of the old data.
So they adjust it to suit their begging the question correlation. Then, Andrew.
No. I don't know how many times I've said it, probably 4 or 5. When they do new surveys with better equipment, they look back at their old data and say, well, does the old data match this, or do we need to just shift the measurement just a tiny bit? And remember, I keep saying they shifted. One of the changes that happened is that some of the data they shifted by about 50 microgals, because they worked out that the old equipment was calibrated off, right? Off by 50 microgals compared to the new equipment. So they want to use their data from their old data and their new data and put it all together and make a nice map of the whole lot, and it all being sort of matching, right? So they move some of those 50 microgals. Now, how is that moving 50 microgals causing 100 million microgals difference?
Again, they use the total different. They use the total different gravimeter, as you said.
Yeah, and the measurements produced by at the same location. They've done some of them at exact same locations decades later, and the figure they got from the new equipment compared to the old equipment was within tens of microgals. So
it was different, and it was with correlation. And listen,
every piece of equipment is different. You take a different ruler to a different piece of timber, you'll get a different measurement, because equipment is a little bit different. You won't get one ruler saying a piece of timber is 275 millimeters long and the other one saying it's 350 millimeters long. You might get a millimeter difference. In this case, we are talking 15 microgals out of a billion microgals difference. So one piece of equipment versus another, there are some minor differences. Equipment gets better, gets more accurate, gets more precise, and a new piece of equipment gets a same answer at the same location within a billionth of the measurement of the old equipment. So this stuff is highly precise, and you're still not coming up with any reason why there is like a 0.5% difference across the north-south spread of Australia
again,
for these things that are measuring down to 7 decimal places.
Again, I've told you there's many things that the problem. If you're building your foundation,
But do you think geoscientists don't know this? Do you think geoscientists don't know what a magnetic field is and whether it needs to be accounted for?
When the guys build the gravimeter, okay, and they have the input data in the system because it's electronic, do they have? Do they have their how can I put this? Consistencies based on already the data that they assumed to have existed. So in other words, they're building their foundation, so they don't have data, a reference datum that they've already planned for the baseline in that system.
It's an absolute gravimeter. It measures absolutely, with reference to nothing else, the rate of acceleration of the fall of the mass in the tube.
In latitude. So when you use a gravimeter, you put latitude in there. You do know you put latitude.
No, you don't.
Don't you put latitude in?
No, an absolute gravimeter. So these readings of 900 million microgals are the absolute measurement. This is like the raw reading out of the thing. It measures the thing falling 200 times. It could be once. So they measure it doing 200 times and they haven't average it. But it is the measurement of the rate of acceleration. And the difference between the 200 drops might be 10, 20 microgals, and they average that out because there's going to be experimental variation. Over the course of a day, they do 2,000 drops and they average them out.
Would you quickly go and maybe find something where they show how they use a gravimeter, absolute gravimeter?
They take the mass to the top and they drop it, and they have a laser measuring.
Not that simple. They actually put some data in before they drop it, mate. So
well, you tell me. You've obviously researched it.
They actually set their latitude, mate.
In an absolute or a relative?
In the absolutes. It's electronically based. That data reading, remember, it's interferometry. They have to have it electronically reading that dropping mass.
So why does latitude make a variation in what how the
because they put the data in there based on the belief of a globe. The data.
How does latitude affect what how does the latitude affect how the gravimeter works? And why would they have to put latitude in there?
It doesn't affect it. They've set it into the data. You're not getting it. It's already begging it's a rigged system. It's a rigged system.
Fantastic. Okay, Flatzoid, we finally got to it. You are claiming they are lying. Simple as that. You're saying they're lying because. Well, then what?
The manufacturer.
You just said that the gravimeter has a latitude setting, and the implication is that by setting the latitude, it puts the latitude variation into the data.
Listen what I'm saying. No one's lying. To be lying, they literally have to be knowing it is and deceiving it. They're not there to deceive anybody. When they do the manufacture, they have certain correlation data points they have to stick in. Those correlation data points are already based on the assumption of a rotating geoid.
Okay, Flatzoid, what other assumptions do they put into the equipment so that they can tease out the geological variations? What other things do they have to program into it?
I'm not a gravimeter
Right, okay. So in order to do that, they not only have to put the latitude, they have to put the longitude, they have to put the altitude. The entire piece of equipment would have to know the topography of the entire Earth, because those are the variations, those are the things that are taken into account and weeded out of the data in order to find the geological variation. So can you tell me that clunky old 1979 Soviet gravimeter has an entire topological map of the Earth in it in order to push in the Bouguer anomalies? Do you really think that equipment has that in it?
Again, that's electronic.
The fact is you don't know enough about how they work. You don't know about how the data is teased out to get the geological variation. You are just making things up. You're claiming they're programming the data into it. Absolutely you are.
Okay, you don't even
Smirk
know.
on my face because you're just not coming up with any explanations, Flatzoid.
First of all, you the one that came up with the claim. It's not my burden to prove. I'm just chatting to you about it, trying to say your claim doesn't hold.
Flatzoid, these
Doesn't
things
hold
fall in
water. Your claim doesn't hold water because there's many variables that it could be. I'm just trying to show you based on your claim why it could be wrong. It's not my burden.
So what about?
It's not
what
my
about
burden. Can I
the-
stop talking? Can I carry on
Okay,
talking?
go on.
It's not my burden to be able to make the claim for you. You made the claim that it's gravity. I'm telling you why it's not gravity.
I make a
Because,
claim that there's a variation with latitude.
and I never said there wasn't. The point
Right.
is.
So how
the
does
point
relative
is,
density disaggregation explain that?
again, your claim, your burden of proof, not mine.
No. That data, that rainbow graph of Australia, that's the absolute data. There's a variation, and you're not denying that there's a variation.
Based on correlation data.
No. That is just the data.
In other words, rigging the game.
Not at all. Those are the 1.4 million actual measurements. There's also satellite and aerial gravimetry done to fill in. That's why the oceans are also covered, smoothed out to make a nice, pretty picture. But that is basically, if you took that data, like I did in the graphing I did in my spreadsheet, if you took that data that they published from those 1.4 million actual measurements and put colours to them and latitudes and longitudes to them, you would come up with that exact same picture. So the raw measurement says that there is a large-scale variation, and it just happens to look like latitude lines. So there's a reason.
That means globe then.
Well, it's a good evidence.
And that means
gravity.
that means gravity then.
It's a good evidence that there's a high correlation between latitude and the change in gravity, and that matches the model. You claim that things falling, high correlation. There's nothing problem with something with being highly correlated as being evidence that there is a cause between them. Now,
correlation is not evidence of anything. Correlation is just showing you have a
fine.
bias.
Talk to statisticians about that if you want. But you are claiming that things fall because of relative density.
And that can be proven experimentally, yes.
In these absolute gravimeters, the same mass with the same density in the same evacuated tube with the same medium is dropped in hundreds of places, literally 1,000 places around Australia, and it gets different answers. So what is
it even gets different answers in exactly the same area. You literally
within
said
an extremely small level of precision.
So they have to make an average.
Yes, that's what I keep saying. A variation of 15, 20 microgals in an absolute reading of a billion microgals.
The point is,
there you go. If it's not perfect, it's not right.
No, the point is the variables are not taken into account.
What variables? What variables need to take into account?
You can't
Okay, you're saying it's rigged. You're saying they're plugging in data in order to get the right answer. No, they're not. They're measuring a mass falling. They are publishing a 9-digit long measurement of the rate of acceleration of that mass. It varies clearly correlated with latitude. You have no explanation for it.
Because I didn't make a claim about it. I don't need to have an explanation for it.
Well, I'm presenting you with a whole lot of data, and I'm asking you, how does your paradigm explain this data? My paradigm explains it perfectly. My paradigm explains it so well that if you take those variations by latitude, centrifugal force, Bouguer anomalies, blah, 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 you can find that there's diamonds here and there's gold here and there's oil over here. You're looking at those numbers. I present this data to you, and you can tell me no explanation of why there are these huge variations.
It's like me presenting data on why a donut has a hole in the middle, and I'm telling you, please present to me data why you say in your paradigm that there's a hole in the data, in the donut.
Does the globe model say that donuts should have holes in it? Is that part of the paradigm?
So does relative density disequilibrium claim that there should be variations at latitudes?
Well, relative density disequilibrium says that it's just the mass, the object, and the medium. And the object and the medium in this one gravimeter is the same. And you take it to different locations, and it falls at different rates.
Again, so, many different variables at play.
Right. Well, then what is it causing a variation in like a 0.5% or whatever it happens to be? What is the variation across the Earth that seems to correlate with what we call latitude that causes such a large variation in the rate of fall of that mass?
Again, I said it could be many things. No one's making the claim, so it's not my burden to back up. You're just telling me...
Well, there you go. You've got no explanation, and you're telling me you don't have to give an explanation.
Because
so there
it's
you go.
not my burden.
I've presented data that correlates fantastically with latitude, and you can't refute it.
Again,
so that's it. Fantastic.
Again, no one has ever claimed that there is not variations at latitude.
Well, then what's your explanation for it?
So that's literally just a straw man and a red herring.
What's the explanation? Why does it vary from 9.78 to 9.81 across,
because I'm not the one who
northern
brought...
Australia to southern Australia?
I'm not the one who brought...
What's the variation? You're not denying that the data exists. What's your explanation for the variation? Yeah, keep talking. That's no problem.
You're the one talking over me, mate.
That's all right. Give me your explanation.
You're the one who brought the argument up. It's your burden. You brought the data based on your correlation that it's a globe.
No.
And I explained to you the data is based on begging the question, affirming the consequent fallacies. The mechanics behind the gravimeter already has the corrections made based on assuming a rotating spheroid. Okay?
So have you got something to back that up?
Yes.
You've got something to back it up, that they take the gravimeters and they program their latitude. Now, they've got to program their longitude. They've got to program the entire topography of the Earth because they've got to do the free air anomalies.
So they do program in their location then?
No. You said they do. I say they don't. They just take the mass and drop it and measure how fast it accelerates. You're saying that they program the latitude.
So I can take a PVC pipe, make a vacuum out of PVC pipe and just drop a cork in it, for instance, and take a measurement at every latitude I want to? Is that what you're telling me?
Well, how precise would that cork in a PVC tube be? Is it one microbar in there? What are you going to use to measure the rate of acceleration?
I'm just saying, that's what you're saying. They just take it and drop it. So that whole electronic system they have placed into it is just not needed because they just take it there and they just drop it.
That's the measuring equipment. That's the interferometer and no doubt an atomic clock or something. Well, not an atomic clock, maybe a really good quartz clock that's doing the really fast measurements and the really precise measurements of the mass as it falls, and therefore teasing out the acceleration of that mass. The actual mass itself it's so simple. It is just a mass dropping. Right? They do it in a vacuum tube so that the variation, you don't have the air affecting it, and they just measure how quickly it accelerates. It's as simple as that.
Okay.
And the data says, here's the data. If I present this data across a million measurements across Australia, and I put colours to the strength of gravity, look at this. The data looks like latitude lines. Now what have we shown? The color can be calibrated by the difference in measured gravity. Right. So what would be the difference? That's interesting. Okay. So what would be the difference between rotating a gravimeter around and different Coriolis effects for it? At what level? Is it 100 million microgals? Is it 10 million microgals? Is it 50 microgals?
I don't know. You said that I don't know what I'm talking about.
Well, you've just brought up a claim. You've just brought up some information that
what
says
I'm saying. You
just said can vary because you rotate them.
You just said
Is that going to produce 100 million microgals difference?
You just said I don't know what I'm talking about and that they don't use it for calibration, and then I just brought it up to say they do. So I think you should have done your homework a bit better.
Can you bring that up? Hang on. Can you bring that up again, please?
Okay.
All right, it's a little bit small. I couldn't read it.
I'm going to bring it up now. Add to stream. The Coriolis effect atomic can be calibrated by rotating the gravimeter for 180 and back to obtain the difference of the measurement G value. So they do calibrate it.
Do you know what that's... No, it's the other way around. It's the other way around. It says you can use an atomic gravimeter to measure the Coriolis effect by rotating it. That's fantastic.
So they already got
Thank you, Flatzoid. Oh, law of Flurf number 1, you've just debunked yourself.
Are you seriously this dumb?
It says
they
the calibrating of a gravimeter can be calibrated by rotate. Right. So it's the atomic gravimeters. Now I don't know much about atomic gravimeters. I've only looked at free fall ones. They are so sensitive that the Coriolis effect can affect atoms falling through a cloud. Now, I don't know much about atomic gravimeters, so I can't really talk about that. But it's obviously they are so finely precise that Coriolis effect can be measured by it. So if that has to be calibrated for, that's fine. It's not programming in the 100 million microgals. It is perhaps I don't know what level of effect that has, but it's very possibly in the order of fractions of microgals. I don't know. I haven't looked into them.
There's your errors.
Errors. What are the units there? I don't
Very
know.
low.
It's really small. I don't know what I'm looking at. Sorry, I can't tell you what that is. So I haven't looked at atomic gravimeters. Can't talk about those. But you still got to work out what is it that causes 100 million microgals difference between the north of Australia and the south of Australia.
I don't need
200, 300 million.
I don't need...
That's what the measurements are. And so you're saying that they're programming them in. You've got nothing that says they're doing that. But again, like I say, they've got to program in every single factor. Otherwise, how are they going to, if they're trying to simulate the Earth in order to tease out the geological variations, then they have to program all that stuff in. So the Soviet gravimeter had to have the entire topography of the Earth programmed into it. Otherwise, they're not going to be able to then tease that data back out. You're basically saying they're plugging in data in order to extract that data back out. Well, why plug it in the first place?
Let's do this.
Is it just to perpetuate the globe lie?
Absolute, you said, huh?
I love looking at your search history.
I'm glad you like it. You'll be surprised how much we have to search daily. Absolute gravimeters measure the local gravity in absolute units. We want to say how to use.
Yeah.
But like I said, you made the claim.
I didn't make a claim. I presented data. I've presented data, and I can see that it correlates with latitude. So what's your explanation using RDD? Well, it's highly correlated.
Sorry, did I make a claim of gravimeters with RDD?
Well, I'm presenting some stuff that is evidence for the globe. I'm asking you to explain, because we're dealing with it's evidence based on gravity. I'm asking you how does your explanation of gravity, being RDD, how does that explain what is seen?
Again, they use relative density decimalum for their principle of having a vacuum chamber.
They use RDD.
Listen.
They use RDD, do they? Yeah, come on.
Vacuum chamber, so they varied the medium, correct? They took the medium away, so there's no friction for the object to fall. That's as far as RED goes with a gravimeter. Further than that, did I make a claim about any latitudes or that it should change or anything?
If RDD is just the object and the medium, why does this produce different measurements in different locations? If it is just the object and the medium, then it should produce the same measurement everywhere.
Would you know what an iodide absorption cell is?
No, I don't.
Me neither.
Good. Nice one. Thank you. That made me laugh. Well done.
Okay. I'm trying to read more on it. How do absolute gravitons work, guys? A new generation of absolute gravimeters. This should be interesting.
Yeah, quantum gravimeters. Like I said, I haven't looked at them. Atomic and quantum gravimeters, don't know. But I believe they're the same sort of thing about atoms falling. I don't know.
That's weird. I wonder how they get that working, though. So
I think they might
it's got the dropping chamber.
Sub-gal. Yep.
It's got the dropping chamber. It's got the drive motor. The free-falling corner cuber, drag-free cards.
That lifts the weight again. Yep.
Ion pump. And then it's got the
vacuum pump. Yep.
Yeah, and then obviously it's got the interferometer inside there with the laser, because it shoots up towards the object as it falls down to give the reading. Would this reading also be based on the light being a one-way speed of light?
Oh, don't bring up that. No. Who cares about that? The fact
is the light speed of light?
Red herring.
No.
I don't care.
Interferometry. Interferometry is based on me reading using the speed of light, correct?
this piece of equipment is used in all sorts of locations, and if there was something about the speed of light that varied with location, it would get different things. One, it's the two-way speed of light. It's the light going out, hitting the corner cube, and coming back. The one-way speed of light is just, you know, it's philosophically interesting. Practically, it doesn't matter to us.
It does matter because
know,
it's never been proven.
Well, it doesn't matter.
Yes, it does matter. Is it one-way or two-way speed, Andrew?
It's two-way. Obviously, we're bouncing it off the corner cube.
How do you know? Can you show me where it's proven to be two-way?
It doesn't matter whether the speed of light is the same one-way or two-way.
Oh, yes, it does. Of course it matters.
Not in this equipment. This equipment is just measuring the position of the weight as it falls. Now, are you telling me that there's something about the properties of light that means that gravimeters are not measuring the position of the mass as it falls? That the data is all wrong. Yet it comes out to, you know, all sorts of different types of gravimeters, whether it's using a laser interferometer like these ones, or whether it is the pendulum ones, which is simply timing the swing of the pendulum. They come out with the same answer. Different techniques come out with the same answer for gravity. So, you know, talking about the speed of one-way speed of light, red herring, forget about it.
Why is it a red herring?
Because it doesn't matter. Whether the speed of light is one-way or two-way, this equipment measures the rate of acceleration of an object falling in a vacuum.
With light?
Sure. Do it with ultrasound if you like, but you're not going to get a very fine reading. Do it by taking photos of it every hundredth of a second. You're not going to get a very fine answer. You do it with a laser interferometer because they can get very, very fine readings.
Like I said, there's so many correlations here. It doesn't make sense that you would just say, this is proof of anything. And then trying to push the burden onto me to say, explain this based on relative density when I didn't even bring it up.
Well, I'm providing evidence, and if you can't counter it with an explanation or fights...
I did counter it.
The explanation is, maybe they program it. Well, you got no evidence of that. You got, maybe it's magnetics. You got no evidence of that. So...
Should we look on how to program a gravimeter? How's that?
No, not at all. I'd be happy to move on because my position is that you've got nothing, and you're grasping at straws here about the two-way speed of light, the one-way speed of light. Fine, whatever. Okay, review my performance, review my video, whatever. Tell me I'm a liar, whatever. I've presented data that absolute data from these very, very precise equipments, and when you map it out, there's an extremely good correlation with latitude. And when you analyze the data using the expectation of latitude on a globe, on an oblate spheroid of the size we say it is, you can extract out the very, very small data that says there's diamonds over here, there's oil over here. So, and you've offered no explanation for how there's that huge variation which correlates with latitude and how they can tease out the really small variations based on annulling the effects of gravity, of latitude, of centrifugal force, Bouguer anomalies, without going into the details of those. You've got nothing. I presented data. You can't explain it.
Oh, you're done?
Yeah, I'm done. I know you weren't listening. Don't worry.
I was listening. You were just saying, no, you got nothing. I got everything. I brought data.
That's my position after all that. Do you want to talk about some other things?
What else do you want to talk about? While I search quickly.
For how they program the entire topography of the Earth into gravimeters. Flask task. Your flask task.
Oh yeah, the flask challenge, yeah.
Yeah,
the one which I'm still gonna ask McToon again on Wednesday. When is he going to do it? Yeah, he's going to come debate me on celestial navigation on Wednesday.
You've teed up a debate with him. Yeah, good. I saw that. Fantastic. Love to see it. Your flask task. Well, you claim that the data you've given us, which are 3 distance measurements and 3 angle measurements, are enough to calculate the height of your flask.
Yeah. Well,
that's correct.
That's what you guys are claiming can work with celestial navigation, correct? Because you guys can work out the actual height. Because you guys claim you can work out the actual height.
Yep, that's fine. I've asked you many times.
But before that, I just want to quickly show you on screen here. Sure. Latitude and longitude.
Right.
So they
Yep.
set their latitude and longitude for gravimeter?
I don't know. Or is that perhaps just to put that data in against their measurement, like against their data point?
So
saying
they put their elevation, they put their latitude, and they put their longitude in. So
Okay. Does the CG5
does the
autograph...
data, does that data have a set base? Because they've already put their latitude. Would you need... No, this is my question. Would you need to stick that data in, like latitude, longitude, and elevation, if it was simply just physically based on the gravity reading, as you put it?
Okay, so the question is, does the autograv do some of those? Does it do some of those corrections already for you? And then instead of having to take that raw data, put it into another computer and do the anomaly calculations, does it just do that automatically for you within that piece of equipment?
If it's already got the piece of equipment having the correlation data for assuming it's a rotating spheroid, yes, it would mean it's a rigged system.
So the autograv there, if that's how it works, and I don't know how it works, I presume it could give you the absolute reading and it could give you a corrected reading. So it's doing the corrections already in that piece of equipment.
No, but that's what I'm asking you. Why would they need to put that in if you can get your latitude or longitude based on just taking a gravimeter no matter where you go?
No, you can't get your latitude based on a gravimeter. No, not at all.
Oh,
the
you can't.
idea is that you can get a very coarse reading of your latitude based on gravity, but it's not fine. It's not like celestial navigation where you can get yourself down to a mile or two. The coarse reading, because there's such variations in the middle of the figures due to other effects. You're not going to use a gravimeter to work out your latitude and survey your land. Not at all. So I'm just assuming that the autograv takes the absolute measurement and does some corrections for you. So when you're out there in the field, you can already do the correction based on latitude and elevation, because those are known effects, which you're trying to use that to find out your geology. So you just take out those huge effects straight away from the data. You don't even bother with the absolute measurement. But that machine will make an absolute measurement and then we'll do corrections to it. The same corrections.
Corrections, yeah.
Sure, not a problem. But I don't doubt that you could extract the absolute measurement out of that machine. It'll tell you the absolute measurement and it'll tell you how it's corrected for it. But then again, I don't know how that particular machine works. I don't know how gravimeters are actually used in a practical sense. But if you're going to claim that you're not claiming it, but you're saying that they program that in order to push in the latitude correction into the data, so that later on the geologists or the geoscientists can pull out the latitude correction and find their geology. I don't know how they work.
It works exactly like geo surveys,
so,
geodetic surveys. They take data based on correlations that have consideration that it's a globe. This gravimeter takes consideration that it's a spinning spheroid.
In order to make the corrections. Geodetic servers do not make a consideration.
It's a rigged system then. The data's rigged
it already does the corrections.
It makes the corrections based on its latitude and longitude.
Sure, because we know that makes an effect. How do pendulum gravimeters account for latitude?
Pendulum aren't used today because they aren't as accurate, are they?
Sure. But I still point out the data that was released a couple of years ago that I was using, that 1.4 million data points, that still has data from the 1950 to 1951 to the mid-60s for those 250 original measurements of gravity in Australia using pendulum gravimeters. That data is still there. That data was still in my plot, that curvy plot that I showed. So they may not be as precise, they may not be a little bit less accurate, but the data is still good enough to be used in what's known as the national data grid, gravity data grid. So,
which takes an assumption of a spinning spheroid.
The pendulum ones, you measure the rate of oscillation of the pendulum. And from that you work out
the Foucault's pendulum.
No, the Foucault pendulum rotates. The
oscillations. It's almost like mixing Cavendish and a Foucault's pendulum together. That's what you're saying.
No, it's the speed of period of oscillation, and basically the stronger gravity
of a pendulum. So as it's coming back, it's measuring the oscillation period.
It's measuring the period. And if gravity is stronger, the mass will appear heavier, and therefore the pendulum will swing quicker.
Then you haven't heard about inertia, then, have you?
Do you think that the people measuring the period of oscillation of pendulums don't know what they're doing?
If you take two different objects of different masses and drop them, do they fall at the same rate, Andrew?
Does the mass of a pendulum... is a pendulum...
Take a bowling ball and a basketball.
I'm going to restart there. No, Flatzoid, does a pendulum's oscillation period depend on its mass?
Yes.
No.
And its length.
Length only.
Length and mass. Andrew?
No.
Yes.
Not the period. The amplitude?
Okay. Let's take a pendulum.
Sorry, Flatzoid, you're
wrong.
Let's
take a pendulum with a 10-gram mass, okay? And drop it. Is it going to fall as fast as a pendulum
The period of oscillation.
With a kilogram mass on it?
The period of oscillation will be the same. Go look up a pendulum formula. If
the length is the same, yes.
Yeah. So the mass at the base of the pendulum doesn't matter.
Will you have more oscillations if the mass is greater?
No.
So it won't have more energy and oscillate longer.
The period of oscillation is the same.
I don't
Go look
think
up
you
a pendulum
understand
formula and tell me where there's mass. Tell me where there's mass in a pendulum formula.
So they don't need to put mass on them, so no gravity attracting
No, I didn't say they didn't have a mass. The oscillation is not affected by the mass.
So not mass attracting mass then, Andrew, which is you claiming gravimeters to be doing.
The period of a pendulum, is only affected. Well, it's actually affected by two things. In a normal situation, you don't even think about the strength of gravity. But for a pendulum gravimeter, the amount of mass at the base on the bob of the pendulum doesn't affect the period. The only thing that affects the period is the length of the pendulum and the strength of gravity.
Again, no mass, so therefore not mass
No,
attracting mass then.
I didn't say there's no mass. I'm saying the amount of mass that you put on the bottom of the pendulum does not affect its period.
So then it's not mass attracting mass then?
No, it doesn't affect the period.
Would it affect the period
and I'm sure
if it was mass affecting mass?
Childish people laughing because I keep saying the word period. The period of oscillation, yeah, that's all right. Sorry. The period, I'll say knob later on if that would make you happy. The period of oscillation of pendulum is not dependent on the mass. You put more mass on it, it'll still oscillate at the same rate.
So not mass attracting mass then, Andrew?
No,
not gravity then?
If there was no mass at all, the pendulum wouldn't oscillate. There has to be some mass.
The pendulum itself has mass, correct?
Yeah, well, in theory, pendulums only have a mass at the bottom, but obviously in practice they do have a mass at the bottom, and the actual swing arm has some mass. That's true. But the amount of mass at the base, as long as there's a mass imbalance between one end of the pendulum and the other, it'll swing. Well, if you let it go, it'll keep swinging. But the amount of mass...
So it has momentum then, you'd agree, Andrew?
What's that got to do with it? Yeah, and it gets up to the top of the swing, it loses its momentum, and it gains its momentum again.
So it's got inertia.
Yeah, whatever. I'm sure you're going to say it's got impulse as well. So it's not
mass attracting mass then, it's just simply mechanics of a moving pendulum.
What causes a pendulum to oscillate?
Movement.
What causes the movement? Movement doesn't cause movement. What causes the movement?
Because
the mass wants to go down.
The unbalance.
The mass wants to go down. The mass wants to go down, doesn't it?
The unbalance, yes.
Right. So if you take a pendulum of a certain length...
Listen, so not mass attracting mass, it's the unbalance of the pendulum which causes the oscillation. Do you understand what you're saying?
The amount of unbalance doesn't matter. So back to the point, pendulum gravimeters, no mass in a tube, no speed of light, just simply measuring the time that the pendulum takes to oscillate. So where in that are they programming latitude and longitude and topography, Bouguer anomalies, blah, blah, blah? They're not. They're just measuring a pendulum. And you take a pendulum, in the early days of when clocks started to become fairly accurate, pendulum clocks started to become accurate, they took them to different locations around the world and found that they moved at different rates. You change latitude of your pendulum clock, and it will speed up or slow down.
Again,
And that's that's what's happening. That you haven't changed the mass. You've just moved the pendulum, the clock from, I don't know. Actually, one of the early ones was the French. They moved it from Paris. They had a very accurate clock, and they moved it down to French Guiana in South America, so close to the equator. And they found that it varied. I can't remember which way. I'm sorry. It varied one way or the other by like a couple of minutes a day. It was a really, really big variation. And what was the explanation of that? Well, gravity is different at the equator compared to Paris.
So correlation again. What were those gravimeters made out of, those pendulums? What was the brass or copper?
Probably
or
brass.
Gold?
Who cares? Doesn't matter.
Like I put in the earlier, and I told, do you know anything about diamagnetism, Andrew?
So they still variated. Still, the measurements done by the pendulum gravimeters in Australia is still good enough to be compared to the current stuff done by free fall gravimeters and atomic gravimeters, whatever. And it still showed that variation across latitude. It's still part of that data. So the fact that it's you're claiming there might be some other sort of effect going on. Well, is it measuring the variation in diamagnetism across the Earth? I mean, that's an interesting claim, but it's not backed up by any actual measurements of magnetism across the Earth.
Again, if you understand diamagnetism, you would understand it has more plausible explanations on why it would have variations compared to a force that's not a force, that's only in fourth dimensional mathematical constructs.
Yes, of course, I forgot, sorry. Look, you're still grasping at straws, Flatzoid. The variation, I keep saying this, the variation is shown, it correlates fantastically with latitude. Absolute measurements done by all sorts of different equipment is done that shows variation by latitude. It's explained by the globe. It's explained by the globe, but you've got nothing. You've got no way of explaining.
Why is it explained?
Well,
what makes it explained by the globe, Andrew?
Well,
you just said variation,
yep.
Therefore globe.
Yep, because the variation matches the expected variation of the globe. You make a prediction based on the globe, and that's actually what MC Toon's gravity challenge is about. Predict what gravity is going to be anywhere on the globe, and the basis of it is gravitational attraction, the M1, M2 on R squared, that stuff, universal gravitational constant, the mass of the Earth. Make a prediction based on latitude, based on the shape of the Earth, WGS84, for example, based on the speed it's spinning, once a day.
WGS84, you do know that is just correlative based of taking consideration that it is a globe after using planar survey, which is measured flat.
WGS84 is just an ellipsoid. It's an ellipsoid with a certain dimensions. That's all WGS84 is. Who cares where they got the data from?
Clark Kent ellipsoid, yes.
No. The Clark Kent ellipsoid, yeah, Superman's ellipsoid. No, which Clark one? Clark had plenty
I think it's
of them.
Clarkson Kent or Mark Kent. It's one of those two, but it's ellipsoid based on
Clark. There's Bissell. They're different ellipsoids. They're very, very similar. I mean, so
again, that correlation is because they believe it's a globe. They measure slope angles from a horizontal baseline and then calculate on their correlation of belief consideration of an ellipsoid to make it into a globe. That's exactly what it is.
We've delved into spherical excess, which is one of my favourites. But anyway, can we go back to the flask task, please?
Go back.
That.
You want me to show you? You want me to show you the measurements and distances again?
No, it doesn't matter. No, I know the measurements and distances. I've asked you: is it 1.01 meters, as your graphs say, or is it 1.1 meters, which is what you have vocally said? Sometimes when you measure
1.01 actually.
Okay, because you've said 1.1 a few times.
I meant 1.01.
Yeah. Okay, good. Thank you for that clarification. Now, the problem is with the information you've given us is it's not complete for something at such a small scale. Large scale things like when we say that on a flat Earth you could calculate the height of the sun, that's because the observer height is insignificant compared to the height of the sun. The height of the sun might be thousands of miles. The observer might be a couple of meters tall, not a problem. Your flask is potentially only about twice the height of your observer. So your observer height is important, and you haven't told us that. And
my observer height is on the floor. It's level.
No. Is your camera on the floor?
The phone's on the floor.
Yeah. Phone.
Inclinometer.
No?
So when you use an inclinometer, it measures a what? Like a protractor, an angle from the floor?
Yep. No, it measures an angle from the camera, from the horizontal of the camera. So you need to know the height of the
It's
observer.
calibrated
So your
to it's calibrated to the
No.
floor, Andrew.
No, it's not. It's calibrated to horizontal.
Okay. So
okay,
if I'm
no, I will
horizontal
just-
on the floor and I
But what's
go
your-
up,
what's your-
it would be like a protractor giving me an elevated angle. I thought.
hang
Listen. Hang on. I thought you guys said when it comes to celestial navigation, elevation angles don't worry about the surface, correct?
Yes, but you're not. You remember?
So same
I
thing
remember,
then?
No, you remember I said that the scale is important. So I am going to. I'm just going to present a very, very simple using your program of choice. If you could present that one to me to the screen, please.
Yep. There we go.
Okay, so this is my little using MS Paint. Your camera is the red thing on your phone is the red thing on the left. So obviously the camera is not on the floor. It is 10 centimeters or so above the floor. Do you agree with that?
Okay.
Yeah, not the exact measurement, but you do agree that the camera is not actually on the floor.
No.
Good, right. So your app that measures the tilt angle of your camera, that is measuring that angle, and I've shown that in green, from your horizontal of your camera. So it is measuring from wherever your camera is pointing directly, roughly halfway up the flask,
So
to the
triangle.
angle to in your, and it measured it to, not to the top of the flask, which is again something we didn't notice at first, but it is measuring to the base of the lid. So
where we were talking about Polaris, yeah, that would have been Polaris on the flask.
Right. Yeah, you did your measurements from the base of the lid, not from the actual top of the flask. So I've got some annotations. You can see this next one. So we've got the floor distance, the elevation angle. On the left, I've actually shown the effect of tilting the camera backwards. It will actually drop the camera, tilting the phone backwards will drop the camera ever so slightly, not very much. But we need to know, if we look on the right, we need to know the camera height. That's the lower part of the flask. We can calculate the green section. I've called that the elevation angle height. That's the height we've calculated from your elevation angle and your floor distance. And to calculate the total height of your flask, we need to work out how high the lid is. And that's what we've been trying to do. And as you're probably aware, another one of your resident trolls has done that. Mascro did, and made some guesses and assumptions and came up with some answers. And you said that Mascro was wrong. But at least they had an attempt at working out what some of these numbers were. So can you tell me, with the information you've given us, which basically is just that purple floor distance and the green elevation angle, how we are supposed to calculate the height of your flask from just that information given?
Great, I'm so happy you brought this up because you've just made my whole point that I was making. In celestial navigation, when we take a sextant reading to the apparent angular measurement to the star, we do exactly what you just showed here. Have an elevation angle. Our sextant is not buried into the ground. Okay?
Sure.
Correct. So that's why you do a height of eye correction to make it more accurate. You would agree?
Okay. Have you given us a height of eye correction to your flask?
Sorry. Do you have to give the height of eye correction when you do it, or is it just automatically there?
When you do celestial navigation,
Yeah. You have
you
an
need to know the
almanac.
height. Yeah, you need to know the height of your observer. You haven't given the height of your observer.
Okay, cool. Now, if I give you the height of eye observer, would you be able to correct and get it correct?
Well, then that's what Mascro has done.
No, he got it wrong.
Well, he got it wrong, sure. But that's because you haven't given him the information. He took a guess at the height of the camera, which is this red section, and then using the trigonometry, worked out the green section. And then using relative heights, pixel counting, worked out the blue section, the lid height, and came up with an answer.
You're missing
and
the
also
point altogether. You're missing the point altogether.
Yeah, go on.
When you do celestial navigation, you are not embedded into the surface. So you have elevation angle. You are above. You've taken your apparent angular reading to the star. So that's practically what I did here. Okay?
Yep.
I gave that
Hang on,
apparent angular
wait a
reading. Wait. I gave that apparent angular reading just like you would in celestial navigation. Now you can work out your distance by doing simple trigonometry like we did. You know, doing the internal angles of a triangle. Okay? Right. The 90 minus the apparent angular measurement would give you your co-altitude angle, and that would be times 60 to give your distance in nautical miles. Now, I did the shortcut and already gave you the distance and the angular reading. So that's 2 part of the triangle, correct?
But you haven't given... Now, the difference
I've given
is
you
you've
the
given an elevation...
hypotenuse. I gave you the hypotenuse, and I've given you the adjacent. All you need to do is
Right.
give the height, correct?
Yeah, and all we can do is calculate the green height
So
of half your
no,
flask.
let me finish. So with celestial navigation, I now have the adjacent, the distance, and I have the hypotenuse, which I measured. Tell me again,
The hypotenuse. How did you measure the hypotenuse?
the apparent altitude angle, that's your
That's not the
hypotenuse
length
reading.
that's not the length of the hypotenuse. That's the angle.
The angle is the hypotenuse, Andrew.
Angle to the hypotenuse.
Yeah. So you
Okay, that's
measuring
right.
that, you got that information and you got your adjacent, correct? So
Yep.
would you be able to complete your triangle with that information?
Yes, you can, and indeed we did. We
listen-
calculated the size of the opposite side.
Great. So you would agree then, and you would say, okay, therefore the star that I measured would have to be a certain height.
That's how it should work on flat Earth, should it not? But you can claim that it's not the case.
No. The point is, my flask is demonstrating it's not giving you an actual height. It's an optical apparent angular reading, therefore not at a physical height, Andrew. You've literally just validated my argument.
You've given us the elevation angle. We can work out the green section of height. If you give us the camera height, we can work out the red section of height. There's nothing geometrically, there's nothing in geometry that says that we can't do that.
Okay,
So-
then I've given you
What-
the
so then the
adjacent.
que- so-
Listen, I've
so
given
then
you
the
the
question is
adjacent.
what-
I've given you the adjacent and the hypotenuse, just like we have in celestial navigation. Give me the height, please.
I don't have the numbers off the top of my head, but between your three different measurements, it gave three different heights of the flask, and that seems to imply that either geometry is broken or your measurements weren't very accurate.
Or distances show not an even amount of linear fashion, as you put it, with measurements on a flat surface, because it changes. It's not as linear as you guys want it to be.
I don't know what you mean by linear in that sense.
Linear. You guys always moan that if it's on a flat Earth, it wouldn't be linear
So
distances.
if you double your if you increase your distance linearly from the flask, the angle to the flask will not vary linearly. It'll be a trigonometric function on a flat surface.
So I went 1 meter and 1 centimeter, correct? Is it 1.01? Then it was 2.02, I think, and then 3.03. So that was linearly, correct? And these are the measurements they gave at each one.
I've got your measurements there. Now,
Yeah,
is the difference between between those measurements a linear amount?
So did the flask actually change height?
No, of
or
course
was
not.
it optical?
It's the apparent height change, but you'll see that it doesn't change in a linear fashion. The difference between those three angles, those two gaps between those three angles, is not a linear amount. Yet in celestial navigation, you move a linear amount and multiples of that linear amount. Your angle to the celestial object will move also by a linear amount. This is not a linear relationship. The Earth isn't flat.
Oh, so in other words, parallax then, Andrew, because you've said as well, if something's
parallax?
far enough away, far enough away, it would seem more linear, correct?
You don't understand. You have a different definition of what parallax is.
Oh, really? Okay, a mountain at 100 kilometers away and a light post at 10 meters away. You move. Which one is going to be more apparent in angular size change and location?
No. Parallax is side to side.
Parallax
it's not
is
when you move forward and backwards.
only side to side. Take a water bottle with a water line in it. Look on top of the water bottle and move your position down to underneath it. That's parallax, Andrew. It's not just side to side. Whoever said parallax is only side to side is very ignorant. You've just literally validated my whole argument. Well done.
It's not moving forwards and backwards, towards or away for something. Anyway, so your end result is that with the data that you gave us, you actually can't say that what the height is. So there you go. We're left with incomplete information.
Just like celestial navigation, not the height of the star then. Apparent altitude angle. So when people come with straw mans, we need to know the height of the star, therefore it's not a flat Earth. You just proven it's not.
When you do the geometry, the actual physical location of the star moves depending on where you are standing, which obviously physically not apparent. The actual, this is what the geometry is trying to work out, the actual location. I mean, just
the
like
geometry shows it's measured flat, and it's an apparent. You just proven you can't get the height. You've made my point. You can't get the height.
I made your point that you haven't given us enough information for your flask task.
I gave you the same information you have with celestial navigation, mate.
Yes, and we told you the height of the upper half of your flask.
So it's
weird how
it's weird how you can get the height of a star with celestial navigation with the same information, but you can't get the same information right with a flask.
Right. The star is potentially tens, hundreds, thousands of miles up in flat Earth. Your flask is only twice the height. Well, that's what the geometry says. The flask is only about twice the height of the observer. The observer height is very important when the ratio between the two is so close. And you haven't given us the observer height.
Parallax makes a difference then?
That's not parallax.
Yes, it does. Parallax.
That's offset via observer height.
Parallax makes a huge difference. When something's further away, the angular size change and angular distances location
So people measuring the height of buildings
will be much different than something that's closer towards you. The amount of change.
People measuring the heights of buildings, the heights of trees using trigonometry are not getting it right. Not a problem. Geometry is broken.
Did you see that video when we had those two math boffins trying to work out the radius based on the shard? The shard where they stood.
Oh, Matt Parker and Hannah Fry.
And they got it wrong?
No, they got the height of the shard pretty good for the really crude measurements. They got the radius of the Earth wrong.
Right,
no, they got the. No, I know that. I'm a fan of Matt and Hannah's. Now they got the radius of the Earth wrong because they weren't allowed to bring their huge protractor. They had a huge laser cut protractor. The thing was like a meter big. I don't know. They weren't allowed to bring it in. Security wouldn't allow them, so they had to just use their phone to take a very crude measurement of the dip to the horizon. They actually calculated the height of the shard really, really well based on just pacing it out and the length of Matt's feet, I think it was, and measuring angles up to the shard. They did that. That geometry worked really, really well.
And when he measured up to the shard, did he get the shard's height 100%?
Well, of course not, because it wasn't, they were measuring his footsteps. Right?
Great. So when we measure...
So when they got the height of the shard to within a few meters, and they were trying to get the height of the observation point, not the top of the thing, and can compare that to information about the building, and they got it within, I can't remember, a few meters. They got it pretty close. So geometry works fine. It's just their measurements weren't precise enough.
So if I take a sextant and I measure a very particular, let's say a lighthouse, and I do a measurement, and I know the height of that lighthouse, okay, and I complete my triangle. I can do that. I can complete the full triangle to know my distance from the lighthouse.
If you know your distance from the lighthouse, you know the angular height of the lighthouse, you can then work out what the actual height of the lighthouse is.
So completing a triangle.
Not a problem. The question is it far enough that the curve of the Earth makes a difference?
Great. So you just conceded then we use triangles. We are able to complete triangles.
No, we don't. No, we don't.
So
that's triangulation to work out your position based on known shore features. Celestial navigation is trilateration, where you work out your position based on your distance to three locations.
So
you don't complete some triangles in celestial navigation.
So when you do a horizontal sextant reading, well, you love the horizontal.
Yeah, that's.
Do you do another triangle?
That sounds like dirty talk from you, Flatzoid. Do you love the horizontal too?
I do, yeah.
Good to know. Sorry, we are both children. We are both children.
Yeah, we at least have
when
fun.
When you're doing a horizontal sextant measurement, you're going to be completing a triangle to a couple of known shore locations, and you are going to be triangulating your position. Yeah. You are going to be completing a triangle. When you do the vertical sextant measurements and work out your distance from a GP, You were doing trilateration. You were working out your location based on 3
Triangulation is based on angular readings to work out your distance.
No. The important thing is not the angular reading to the star. The important is the distance from the GPs.
What do? We use the angular reading to work out our distance. So it's triangulation, Andrew.
No.
Trilateration.
So the angular reading doesn't tell you where you are.
Trilateration.
The 3 distances tells where you are.
Sorry, do I know off of my triangulation of my apparent angular reading the distance to that star? How would I be able to do my LOP and my circle of equal altitude? You didn't?
You don't complete a triangle. Where have you completed the triangle when you do your measurement to the star? You don't complete a triangle.
If I take a measured angular reading,
apparent angular reading
of 45 degrees, let's say. Okay?
Yeah, and you're multiplying that by an arc distance across the globe of 60 nautical miles.
I take 90 degrees, I minus 45 degrees, it gives me a co-altitude of 45 degrees. I times by 60, it gives me my distance from the GP of that star. Now
and then you use 3 distances. 3 distances.
I triangulated.
3 laterals. Trilateral.
I triangulated. Listen, I triangulated.
No, you don't use your azimuth angle to the star to triangulate your position.
You don't like that word, do you? You don't like that word, do you? I triangulated my distance to the star's GP because I measured an angle.
No, that's not triangulation.
Must I show it on screen for everybody what's triangulation?
No, don't worry. Look, Flatzoid, I think you've got about 10 minutes to go. I've got some we didn't get through the things I wanted to. I've got some quick questions for you, seeing as I've got your attention. Quick questions. Southern Hemisphere long-distance flights. You've said that they are misrepresented. Can you explain that, please?
Sorry?
Southern Hemisphere flights. Johannesburg to Perth. Johannesburg to Sydney. Sydney to Santiago. Auckland to Santiago. Luanda to Sao Paulo. You've said that southern flights are misrepresented. Can you explain what you mean by that?
Yeah, the globe misrepresents them.
But do you agree that it takes about 12 hours to get from Sydney to Johannesburg? 12 or 13 hours?
I don't know. I've never taken the flight, so I can't.
Right, okay. Well, it takes about 12 hours one way, 13 hours the other.
Obviously, people that have flown that say about that, so yeah.
Sure, not a problem. So you've been challenged on, and you say, and your only response has been that Southern Hemisphere flights are misrepresented. And so I don't know what you mean by that. Do they exist? Do they take as long and therefore cover as much distance as is claimed that they are? What's wrong about them? Like, how do you explain them? How do you explain that there's no flat Earth map that explains how you can get from Johannesburg to Sydney in 12 hours in an aeroplane?
No, like I was saying, it's misrepresented by Globies by trying to do strawmans. That's what I'm trying to say.
Okay. So you don't seem to have any problem with southern flights that it takes 12 hours to get from Johannesburg to Sydney. No. So you multiply the time by the speed of the plane, you work out the distance. Therefore, you can probably flat Earth map do you use to show how southern hemisphere flight works?
I don't fly plane, but I use sectional maps for any navigation, like everybody else in reality. So you don't use full-sized globes or whatever. You use a sectional map for where you're traveling.
But the distances around here.
But okay.
Here's Johannesburg. Here's Sydney. The distance around between here and here matches the time and the speed that planes fly.
Again, misrepresenting. Yeah, on your globe. That's what you say.
Well, they do.
Okay.
So
anyway, I just want to show you quickly. I just want to show you. In surveying, triangulation is the process to determine the location of a point by measuring only the angles to it from known points on either end of a fixed baseline using trigonometry. On either end of a fixed baseline using trigonometry.
Yep.
Measuring distances So rather than measuring distances to the point directly as in trilateration. Do you understand when we measure? Can I talk?
Yep,
when we do measure an angle to get our distance, that's triangulation. That's celestial navigation.
So do you measure the known point
afterwards? We trilaterate after we've done triangulation.
No.
Yes.
The known points of the GPs. The known points of the GPs, and you know your distance to the GPs. You don't measure your azimuth angles to the GPs. You determine your distance to the GPs by some method, whatever that method is,
angular
and then you trilaterate. Well, that's fine, but you're not triangulating their location.
You triangulate.
Well, if you're triangulating their location, then you know the height of the stars, and the height of the stars aren't consistent, and it all falls apart. We're really running out of time.
Okay, but let me just
Yeah, go on.
Let me just finish. You triangulate your distance, your position, by having an angular measurement, so you have the distance. Once you have your fix and you have 3 different fixes, then you trilaterate your position. Get it?
Right.
Because
Well,
you
then you
already
just have
have
to show where you're
then you already
triangulating your
have
DP
the
distance.
distances. It's first triangulate, then trilaterate.
Okay, well, you have to show then how you complete a triangle to find those distances. Okay, quickly. Southern star rotation. You seem to have denied that there is a southern pole of rotation.
No, I've never
And
denied
that
that.
yeah,
I
you
said
have.
they
You've done-
don't.
you've done-
I said they don't rotate in the opposite direction, and I said sigma octantis is simply just an arbitrary state in the south to give for southern rotation, which you
but
can
if you
hardly
watch,
see.
if you look, it doesn't matter if you can't. If
Of course,
from
it
your
doesn't matter if you
location,
can't see it.
No, it doesn't matter if you can't see the actual point. In the north, there is a really bright star that's very close.
Polaris.
If you in your location near the Tropic of Capricorn, if you look north, you will see with a time lapse that the stars appear to rotate around a point that is below your northern horizon, and they'll appear to rotate anti-clockwise. You turn south, you'll see a point in your sky that might be 20 degrees above the horizon. That the stars in that direction appear to rotate clockwise around.
It's
that
always
point.
east to west, Andrew.
But it doesn't matter. Anti-clockwise or clockwise around a point.
Always